You ever just look up at the night sky and really wonder what's going on up there? I mean, every single one of those stars is a sun. Some are way bigger than ours, some are smaller, but they're so ridiculously far away, they're just these tiny little points of light. So today, let's get into it, because astronomers have figured out how to read that light like it's a cosmic message, and it tells them everything.
Right. So this is the central mystery we're tackling. How in the world can we possibly know how hot a star is, or how big it is, or get this, how much it weighs? It sounds completely impossible, doesn't it? Well, it turns out that little speck of starlight contains all the clues we need. You just have to know the secret code.
So our whole investigation, it starts with the most obvious thing you notice, how bright a star is. But here's the catch. What we see from our backyard here on Earth isn't the whole story. We've got to figure out a star's true brightness, its actual intrinsic power.
Okay, this is a super important difference. Think about it like this. Apparent brightness is like seeing a single headlight way down a dark road. It might look dim, right? But you have no idea if that's a little scooter up close or a massive truck really, really far away. Luminosity, on the other hand, is the actual power of that headlight. It's the total energy the star is blasting out into space every second. And that's one of the first big secrets we need to crack.
And this is the whole puzzle right here. If we see a dim star, it could be a genuinely faint star that's pretty close. Or it could be an incredibly powerful star that's just super far away. So to figure out its true brightness, its luminosity, we first have to solve for that other big unknown. How far away is it?
And this is how we do it. It's this brilliant method called stellar parallax. You can actually see this for yourself right now. Just hold your thumb out at arm's length. Now close one eye and then switch. See how your thumb seems to jump back and forth against the wall behind it? Astronomers do the exact same thing, but their eyes are the Earth's position in January and then its position 6 months later in July. By measuring that tiny, tiny little jump against stars that are way in the background, they can use simple geometry to calculate the distance. So cool!
Okay, so once we know the distance, we can figure out a star's true luminosity. That's clue number 1 in the bag. Now let's move on to the next piece of the puzzle, because this is where it starts to get really interesting. The next secret hidden in that starlight is the star's temperature.
You're not going to believe this, but a star's color is basically a thermometer. Seriously. It's just like a piece of metal in a forge. First it glows red, then orange, then it gets white hot. Stars do the exact same thing. The really hot ones are blue, and the cooler ones are red. But astronomers have an even more precise tool. They can split the starlight into a rainbow, a spectrum, and look for a sort of chemical fingerprint. Little dark lines, called absorption lines, show up where elements in the star's atmosphere have absorbed light. And those lines tell us exactly what the star is made of, and, crucially, how hot it is. It gives us a really, really precise temperature.
And this is the result of all that work. It's a cosmic thermometer. Astronomers classify stars from hottest to coolest with these letters: O, B, A, F, G, K, M. The O stars are absolute blowtorches, over 30,000 Kelvin. The M stars are the coolest red ones. And just so you know where we fit in, our sun is a G-type star, sitting right there in the yellow range.
All right, so we've got the star's true brightness, and we've got its temperature. Now, for what sounds like the most impossible feat of all, we're going to weigh it. I know, it sounds crazy, but again, the universe gives us a very clever way to do it.
I mean, really think about that. You can't put a star on a scale. You can't get anywhere near it. So what force is big enough, powerful enough, to be measured across light years of space and tell you how much something weighs? Yep, that's it. Just one word. The force that holds the entire universe together is also our cosmic scale. Now, obviously, we can't feel a star's gravity from here, but we can see its effect, as long as that star isn't alone. And here's the secret sauce. About half of all the stars out there are actually in pairs. They're binary stars, locked in a gravitational dance, orbiting each other. And by watching that dance, by timing how long their orbit takes and measuring how far apart they are, we can use the laws of gravity figured out by guys like Kepler and Newton to calculate their mass. It's truly amazing, and it's the only direct way we have to actually weigh a star.
Okay, let's recap. We have luminosity, the true brightness, we have temperature, and for a lot of stars, we now have their mass. We have all 3 crucial pieces of the puzzle. Now it's time to put it all together. This is where our detective story gets its big aha moment, using a tool that's basically a decoder ring for the entire universe of stars.
It's called the Hertzsprung-Russell diagram, or the HR diagram for short. And honestly, this might be the single most important chart in all of astronomy. It's simple. On the vertical axis, you plot how bright a star is. On the horizontal axis, you plot how hot it is, with the hot blue stars on the left and the cool red ones on the right. And when you start putting dots on this chart for all the stars we've measured, something incredible happens.
The stars don't just land randomly all over the place. Nope. About 90% of them fall right along this neat diagonal strip. We call it the main sequence. These are the stable, grown-up stars of the universe, all doing the exact same thing, fusing hydrogen into helium in their cores. Our sun is right there, a solid, middle-class main sequence star.
So what about the other 10%? Well, look up in the top right corner. The stars up here are cool, so they're red, but they are incredibly bright. Now, how can something be cool yet super luminous? The only possible way is if it's unbelievably huge. It needs a massive surface area to pump out all that light. And that's what these are, the giants and the supergiants, stars that are getting old and puffing up.
Now, let's look at the complete opposite case, down in the lower left. The stars here are scorchingly hot, white or blue, but they're incredibly dim. So how can something be so hot yet so faint? Well, it must be tiny, really, really small. These are the white dwarfs, the super dense leftover cores of stars like our sun that have run out of fuel.
So let's go back to that main sequence for a second, because the HR diagram reveals this one profound truth. As you go from the bottom right up to the top left, stars don't just get hotter and brighter, they also get more massive, and that mass controls everything about their lives. The high-mass stars at the top live fast and die young, burning through their fuel in just millions of years. But the low-mass stars at the bottom, they sip their fuel slowly and can live for billions, even trillions of years.
And that, right there, is the big secret we've been looking for. At the end of the day, the single most important thing about a star is its mass. That's it. Mass sets how much pressure is in the core, which sets the temperature, which sets the rate of nuclear fusion. And that, in turn, determines the star's brightness, its temperature, its color, its size, and its entire lifespan. For a main sequence star, mass is destiny.
So we've seen how this incredible chart, the HR diagram, can decode the life of any individual star out there. But that leads to an even bigger question. What happens if you use it to look at a whole family of stars, a giant cluster that were all born at the exact same time? What kind of secrets about age and cosmic time itself could a picture like that reveal? Well, that's a story for another time.